Hey, my name's Neil Ballard. Currently a computer science major at Florida State University. I'll be graduating in summer 2015. Basically, this project is on the A-star search algorithm, which is a pathfinding algorithm commonly used in games. I chose this topic because I'm a gamer myself, and I think it's interesting when you play a game, uh, especially the strategic games. You don't really look at it from a programmer's perspective unless you really want to, and it's quite fascinating how these paths are established throughout the game and how the AI works. And so I wanted to dig deeper under the hood to the topic and see exactly how everything works. To start, we can ask, what is the A-star algorithm? Well, firstly, it's probably the most popular pathfinding algorithm in gaming AI. It's a search algorithm that can be used to find solutions for many problems, but pathfinding is the one we'll be focusing on in this presentation. A-star, it repeatedly examines the most promising unexplored locations that it's seen. When a location is explored, the algorithm is finished if that location is the goal. Otherwise, it continues and notes all the location's neighbors for further exploration until ultimately the goal is found. The A-star, it's based off of two algorithms, one being Dijkstra's and the other being greedy best first search. Dijkstra's algorithm basically works by visiting vertexes in a graph with the starting point, and then it repeatedly examines the unvisited vertexes and adding vertexes along the way to the set of vertices to be examined, and as it expands outwards from the start point until it ultimately reaches the goal. And then you have greedy best first search, which uses an estimate called a heuristic, which is how far from the goal any vertex is. Instead of selecting the vertex closest to the starting point, it selects the vertex closest to the goal. So that's the key in dealing with heuristics. An A-star is like Dijkstra's in that it's going to be attempting to find the shortest path, and it's like greedy best first search in that its use of heuristics to guide itself. Okay, so now what is a heuristic? A heuristic gives an estimate of the minimum cost from any vertex to the goal. It's important to choose a good heuristic when implementing your A-star algorithm function, or otherwise it can just end up being wasteful. The heuristic, it ultimately reduces the CPU cycles by allowing the algorithm to make educated decisions in the traversal of a graph. The heuristic, it can be used to control A-star's behavior, really. There's many variations to this heuristic depending on what sort of graph or just different situations per different games. As you can see in this one, it's using a diagonal heuristic, which would be some sort of modification with the heuristic itself. Some want perfection, others just want something close. So, like I said, it all really just comes down to the preference and your implementation of the heuristic. There's many variations of the heuristic depending on the type of path the game may require, and that's where you shift the balance of the heuristic of either the cost or the start point and the cost there, and that will give the game its uniqueness of the heuristic it uses. Oh, sorry. Okay, so from more of a technical perspective, dealing with the A-star search algorithm, the variable gx used in the A-star, it describes the distance from the start to a vertex, hx being the heuristic, being the distance from that vertex to the goal, and fx being the search priority at x, which is the sum of the previously noted variables gx and hx. The algorithm, it consists of two lists, one open, which is the priority queue, and the other being closed. The open list is a set of all locations adjacent to the already visited and evaluated nodes. The closed list is the set of all locations that have been directly visited by the algorithm. The goal here is to find the most optimal path by looping through the open list and searching for the least f, which again is the sum of gx and hx. And once this is found, the f is popped off the list and its successors are generated, the successors being the surrounding nodes. Each successor's cost is calculated and then it's added to the open list. At the end of each iteration, the node that was popped off the open list is added to the closed list until the goal is found. And this loop just repeats repeatedly until the goal is actually found. So here we have game development. What this is a comparison of this is the World of Warcraft example of a map. The one on the left here is using what is called what is it called? Oh, sorry. Okay, so the one on the left is waypoint graph. Waypoint is used for 2D games, which is a set of coordinates that are referred to as locations. And the one on the right is nav mesh, which uses polygons to represent the coordinate locations on a graph, which is specific for 3D games. The most optimal choice for pathfinding and game development is obviously the A-star algorithm. It ranges from all sorts of games. Mainly used in strategetic games can be the ones most noted, such as World of Warcraft, Age of Empires, Civilization. Age of Empires, it uses a grid to represent map locations. The map locations used in this game are specifically to 2D, which uses waypoint. In the game, you'll be moving military units, which can be similar to moving an object through a maze. In Civilization, the game uses hexagonal tiles to represent map locations, so pathfinding it's applied to control the military unit moving to the desired location through a group of walkable hexagonal tiles. These strategy-based games require thousands of units being used simultaneously, while a first-person shooter game like Counter-Strike, it'll only involve maybe moving a few units at a time. This makes the game environment much more dynamic. It can be hard to provide optimal paths for hundreds and thousands of units at real time. Uses a lot of CPU and memory resources. So this brings out some of the issues of games like Age of Empires, where you might have half of your army stuck on a tree or something. Most gaming engines, they support pathfinding of waypoint and the nav mesh techniques, both 2D and 3D. And as I spoke on a little bit before, A-star does have its flaws per se. Considering its main use is found in strategy games where we need to move many units at once, it can be hazardous if the implementation is faulty, and it could turn out to be wasteful. So basically, memory waste is a huge concern when dealing with the A-star algorithm. The cons of the base of the A-star algorithm, it's what's brought on the many variations that have been developed. As I said, there's many variations. Just to name a few, the D-star dynamic, which runs knowing that the graph may not be consistent, even while the path is still being mapped out. So the path may change along the way, and the path may need to be adjusted. So this is specifically used well for the D-star algorithm. The hierarchical pathfinding is another variation. It's used to tackle separate layers of a graph by splitting up tasks at hand. For instance, in a game where a maze and boulders are a part of the graph, the higher layer may take care of maybe conquering the maze, and the lower layer can handle the boulders. Also, we have the iterative deepening algorithm, which reduces memory usage by having a general answer from the start and iteratively improving the answer to something more accurate by the end. And to close, we have a little video set up. Basically what this is, it's a visual demonstration that I found on YouTube. I thought it was a good example of just the A-star search algorithm going through a grid. As you'll see, it's going through its path and visiting neighbor nodes, making checks until the ultimate path is resolved along the way, and then it shows the path at the end. I'm going to skip ahead because I believe the video just shows the obstacles being presented first. And here comes the running of it. As you can see, it's very fast, but it's visiting all the neighbor nodes, and then at this instance here the official path was established. And that's my presentation. Thanks for tuning in.